Okay, this image represents a rock with some unstable reactive isotopes in it. Okay, these are going to disintegrate. To measure how fast they're disintegrating, we use a quantity called activity. So activity of a reactive isotope is the number of nuclei of the isotope that disintegrate per unit time. In other words, it's the rate of change of the number of nuclei inside the isotope. Okay, so you can use this equation here, where the delta n represents the change in the number of unstable isotopes, and then the T represents the change in time, and A is the activity in a unit called becquerels. It basically means per second. So 1 becquerel is 1 disintegration per second. Okay, another useful number in radioactivity is the decay constant, which is represented by lambda. It's the probability that an individual nucleus will decay per unit time. Here's a table showing the different decay constants for the different elements here. So you can see uranium with a very small decay constant and lithium with a very high decay constant. So that means that uranium will decay more slowly because the probability of decay is low, while lithium will decay more quickly because the probability of decay is higher. Okay, decay constant is related to the activity by this equation here. The activity is equal to the decay constant times the number of unstable isotopes. Okay, so the unit for decay constant is per second in order to get your activity in becquerels. Okay, so you can see the activity is directly proportional to the number of isotopes. So that means if there's more isotopes in a rock, for example, that means the activity of that rock is going to be larger. So for example, let's take these two examples. So if we've got 2.0 times 10 to the 23 atoms and we get an activity of 40 becquerels, after some time, some of those isotopes will have decayed. And let's say the number of isotopes left over is half of the initial amount. We expect the activity to also half, okay? Because if there's less isotopes to decay, then the rate of decay is also less. Another very useful number is the half-life. The half-life of a radioactive isotope is the time taken for the number of isotopes in a sample to decrease to half the initial amount. So after one half-life, let's say 5 days, we would reach half the initial number of isotopes. After another half-life, so let's say another 5 days, then it would half again, and so on. So it'll keep halving each time. Okay, so we also know that the activity is directly proportional to the number of isotopes, so we expect the activity of the rock to also half after every half-life as well. So it keeps decreasing as well. Okay, so we can also define half-life in terms of activity. We can also say the half-life of a radioactive isotope is the time taken for the activity of the sample to decrease to half the initial activity. Okay, here's some examples of some half-lives. So you can see uranium with a very long half-life, so more than 1 billion years. And then you've got lithium with a very short half-life, decays within less than a nanosecond, basically. Here's another very useful equation. It links the decay constant to the half-life, and you've got the decay constant per second here, and then you've got a natural log of 2. Okay, so that's 0.6931, so on. You can just use your calculator there. And then you got your half-life in seconds. Now, if I used half-life in years, then I'd get my decay constant in per years. And sometimes it's just better to stay in per years. But if you're trying to get the activity in becquerels, then it's probably better that you use seconds instead. In this example, we have radium-226, which has a half-life of 1,622 years. A rock is found with 1.5 times 10 to the 12 radium isotopes. Calculate the activity of the rock due to the decay of the radium. Okay, so here we've got the half-life. Okay, and then we've got the number of isotopes here at some point in time. Okay, and then we want to find the activity. Okay, the equation to use is A equals lambda n. But the problem is we don't have lambda, but that's okay. We can find it using this equation here, ln2 over the half-life. So, but because we're on the activity in becquerels, we're going to have to turn the half-life into seconds. So we're going to turn the 1,622 years into seconds. So multiply it by 365 days, 24 hours in each day, 60 minutes in each hour, and then 60 seconds in each minute. So then we've got 1.115 times into 10 seconds. Okay, so now we can put it into the equation here. ln2 divided by the half-life in seconds. That gives us the decay constant in per seconds. Okay, and now we can bring it back to the original equation, A equals lambda n, and put it back into that one, where n here is the number of isotopes. And if we evaluate that, you get 20 becquerels. I'm ignoring the negative because the negative just shows that the number of isotopes is decreasing with time, and that's fine. We know that it's decreasing. Okay, in a sample of radioactive isotopes, 1.8 times 10 to the 5 nuclei decay over a time period of 1 hour. Determine the average activity of the sample. Okay, so activity is the number of disintegrations per unit time. or basically change the number of nuclei over time. So in this case, the number of nuclei decreased by 1.8 times 10⁵, and that happened over 1 hour, which we had to turn into seconds because we want our answers in becquerels. We get 50 becquerels, basically 50 disintegrations per second. Okay, now it's important to keep in mind that this is an average. Okay, why is this an average? Well, if you think about it, the activity is proportional to the number of nuclei. Okay, so as the number of nuclei decreases with time, the activity also starts to decrease with time. So at the beginning of this, it would have been maybe 100 becquerels, and over time it would decrease, but the average is 50 becquerels. Okay, the half-life of radon 220 is 52 seconds. The initial activity of the radon sample was 40 becquerels. Calculate the activity of the sample after 156 seconds. So we know one half-life is the time it takes for the activity of the sample to half, or basically half of the radioactive isotopes to decay. So after one half-life, after 52 seconds, we expect it to be 20 becquerels and so on. So I'm going to firstly figure out how many half-lives are inside 156 seconds. So I'm going to take 150 seconds divided by 52, the half-life. That gives me 3 half-lives. So that means that the 40 becquerels is going to half 3 times. So I'm going to take the 40 becquerels, half it again, and half it one more time. So that means after 156 seconds, it would be 5 becquerels. Another way to think about this is to do the initial activity times 0.5, basically half, to the power of number of half-lives. So in other words, if we take the initial activity 40, times it by half to the power of 3 half-lives, we get the same answer, 5 becquerels. Okay, in this example, we've got a sample of wood containing 1.19 times 10 to the power minus 13 kilograms of carbon-14 and has an activity of 20 becquerels. Determine the decay constant. Okay, so we've got the mass here, and then we've got the activity, and we want to find decay constant. Okay, and we've got Avogadro's constant there as well. Okay, so ideally we want to use this equation here, but the problem is we don't have n, the number of isotopes. So what we can, however, we can use a mass to find that out. Okay, so we can use this equation here firstly to figure out the number of moles. So lowercase n is the number of moles. If you take the mass and you divide it by the molar mass, we can get the number of moles. And then once you've got the number of moles, you can multiply it by the Avogadro's constant to get the number of atoms. So where are we going to find the molar mass, MR, first? So that's actually over here, the 14. The 14 is the molar mass. Okay, so that's if you divide it by 1,000, that's actually in grams 14. So if you divide it by 1,000, you get 0.014 kilograms per mole. Okay, so if I put that into the equation here, I'm taking the mass, which is in kilograms, and dividing by the molar mass, and I get 8.5 times 10 to the minus 12 moles of carbon-14. Okay, then that each mole corresponds to 6.022 times 10 to 23 atoms. Okay, so the Avogadro's constant. So take the number of moles, multiply by Avogadro's constant, and that gives you the total number of atoms, okay, which is a reasonable amount, quite a large amount, but that's what we expect. Okay, now we've got n. Okay, so we can put it back into this equation here with it and solve for the decay constant. Activity is 20. We've got the number of atoms there, so rearrange for lambda. Okay, and then put that in, and we get a decay constant of 3.91 times 10 to the power minus 12 per second.